is going to be delivered by Professor Lajos Molnár from the University of Szeged. Lajos is also a very good friend of us. We met him in 2017 in a conference that he organized in the Bolyai Institute of Mathematics, which is probably the most famous mathematical institute in Europe. It was founded by Hard and Rist. Okay, correct. And so it was a conference, 2017. We met there, very good friends. Actually, in that conference, I met Kenyer Castillo and some other friends. And so we had a great time in Szeged with Lajos. And yeah, we spent very good time in that conference. So we are so happy. I'm grateful to him that he could join us on this wonderful event. And so I'm really deeply thankful to him. So he's going to speak on order isomorphisms between positive definite cones in sister algebras and their applications. So, go ahead.
Thank you so much. I don't know, can you hear me? Yeah, but yeah, you can. Yeah, but you said that then the camera cannot see me.
Well, no, from here I can see you.
Okay. Maybe this way. So I'm very thankful to the organizers, especially to Paco, for the kind invitation. It's really a big pleasure to be here. I enjoy Spain, every part of Spain, I have to tell, but I visited Granada, for example, so this part of Almeria several times, so Andalusia in general, so I feel like at home. So thank you so much. And so I would like to speak about certain isomorphisms between certain parts of sister algebras. Those parts are the positive cones, and those isomorphisms are so-called order isomorphisms. And actually, this is a survey of some recent applications of a former result, which tells that the positive homogeneous order isomorphisms between positive definite cones of sister algebras are automatically additive. So you don't assume additivity. You assume that your transformation is a bijective map preserving the order and it is positive homogeneous. In that case, this is automatically additive. This is the result what we use here. And as an application, we will determine the structure of certain mean preservers, certain isometries. Let's see how much time I will have. So our basic structures are sister algebras, and we always assume that those are unital. And we have the self-adjoint part, the positive semi-definite part, and the positive definite part of the algebra. A positive semi-definite element means positivity, that's the terminology what they use in operator theory. So that means the self-adjoint and the spectrum is non-negative. Positive definite means that this is a positive semi-definite plus invertible. And okay, so A plus is usually called the positive semi-definite cone, A plus plus is called the positive definite cone of the sister algebra, and we have the order, which is of fundamental importance here. This is the usual order coming from positive semi-definiteness. Sometimes they call it the Löwner order. So A is less than or equal to B, if and only if B minus A is a positive element. Okay? And we also have a very important concept, which is the notion of Jordan star isomorphism, also called sister isomorphism. So a bijective linear map. It's important to emphasize linearity here because in our results, we don't assume linearity. So linear map between C-star algebras is called Jordan star isomorphism or C-star isomorphism if it preserves the Jordan product, AB plus BA, and also respects the adjoint operation, okay? Those maps are commonly called as the most important symmetries of C-star algebras. And so the transformations, what we are considering and concerning which we have the result which we will apply, are order isomorphisms. What is an order isomorphism between the positive definite cones? It's just a bijective map preserving the order in both directions. Easy. Positive homogeneity, the meaning is obvious. And there are examples for such maps. For example, if you take a Jordan isomorphism between the full algebras, then the restriction to the positive definite cones will obviously be positive homogeneous order isomorphism. The other type of examples are the congruence transformations. So if you have T, a positive definite element, then this transformation which sends TAT to A, again, when you restrict it to the positive definite cone, it's an order isomorphism, which is positive homogeneous, clear, trivial, easy. And the somewhat surprising fact is that the converse is also true in the sense that there are no more examples for positive homogeneous order isomorphisms in the following sense, that if we have two C-star algebras A and B, and we have a positive homogeneous order isomorphism between the positive definite cones, then it is necessarily a Jordan isomorphism and the composition of a Jordan isomorphism with a congruence transformation. So there are no more good examples. And actually, this result is just a trivial consequence of another result of ours, joined with a Japanese friend of mine. It's about so-called Thomson isometries. I will give the details in a moment. So the main point here is the additivity of positive homogeneous order isomorphisms. So when you have a transformation preserving only the order and respects positive scalar multiplication, then addition is also respected. Oh, so you get it for free. That's a quite surprising thing, at least it was for me. So the topic, the content of my talk was written in this survey paper, which appeared recently in Fields Institute Communications. Okay, so I mentioned Thomson isometries. What is a Thomson metric? This is a famous metric on the positive definite cone of C-star algebras. The original definition is valid, or it's functioning, or not only in C-star algebra, in more general circumstances as well, but here we restrict our attention to C-star algebras. So this is the general definition. You see that for defining this quantity, you need the order and you need the scalar multiplication. Okay? So you see that if you have a positive homogeneous order isomorphism, then this will be Thomson isometry, because the Thomson isometry is defined in such a way. We can give an explicit formula for that distance, and this is this one. So the norm of the logarithm of this complicated product, what you can see there. Why this, and this is a metric. It's not trivial to see that it is really a metric. From this definition, you can see that it is a metric. From this one, it's very difficult to verify. What is the importance? The main importance of this metric is that, believe or not, this is the topology is the same as the norm topology. But with this metric, the positive definite cone is complete. You know, in the norm, it's an open set. It's not complete. With this metric, this is complete. So, for example, you can apply Banach-Fixed-Point theorem and so on, and that's the reason why they use this metric on positive definite cones. Okay, so we were interested in describing the corresponding isometries. What are the isometries? Okay, few examples. Once again, one can easily see the Jordan star isomorphisms when you restrict them to the positive definite cones. They are Thomson isometries. For the same reason, I mean, again, simple, quite simple to see that congruence transformations are Thomson isometries. And there is a third example, namely the inverse operation. So if you take the inverse and you take the logarithm, you will see that this will be just the negative, but because of the norm, it will be the same. So you can easily see that the inverse operation is again a Thomson isometry. And it turns out now we have 3 prototypes of Thomson isometries, and we can see that from those 3 prototypes we can produce all. This was the joint result with Hattori that appeared in Journal of Mathematical Analysis and its Applications. So you see that the statement is that if you have a surjective map between positive definite cones, it is no linearity is assumed. So just an isometry preserving the distance. Then, so this is a Thomson isometry if and only if we have a central projection P in B and the Jordan star isomorphism between the full algebras A and B such that it can be written of that form. What is it? You see the two-sided multiplication, the congruence transformation, and inside you see a Jordan star isomorphism and the Jordan star isomorphism composed by the inverse operation. So from those 3 types of transformations, you can really obtain all Thomson isometries, and this is an if and only if statement. How can we get our result, our proposition, which I mentioned before? This was about positive homogeneous order isomorphisms. We have seen that positive homogeneous order isomorphisms are Thomson isometries. Therefore, they are of that form. But I assumed positive homogeneity. In this part, it's not positive homogeneous because that is the inverse. So that means that this part is not there. What remains is just a Jordan star isomorphism and a congruence transformation. Okay, and when studying, let me point out an interesting fact that when we study Thomson isometries, this was not the way we proved that result. This is an observation what I made after that. Okay, let me first recall the famous Moser-Ulam theorem, which says that if you have 2 norm spaces and you have an isometry between them, linearity is not assumed, just a distance preserving map, a surjective one, then it is automatically affine. And here the proof, the main part of the proof is to show that between norm spaces, every isometry preserves the arithmetic mean. And in that paper by Moser and Ulam, this is done in the way that they characterize the arithmetic mean entirely using the metric of the norm. Entirely, nothing else. And if you follow their characterization, Moser-Ulam characterization, but you change their argument at many places because their structure, a norm on a norm space, concerns the additive structure, which is commutative. And here, this metric, you see that the multiplicative structure is involved, which is non-commutative. So you have to be very careful. But the point is that if you follow the machinery of Moser-Ulam, you change appropriately their argument, you will obtain that you will have a complete characterization of the so-called geometric mean, okay, using the Thomson metric. And that implies that, and this is the geometric mean of two positive definite elements, which is much more complicated than the arithmetic mean, you see. And so you can see that Thomson isometries are automatically preserving this mean, this geometric mean. And okay, as I said, the proof was different. But now the problem naturally arises that what are the maps between positive definite cones which preserve the geometric mean, okay? Because every Thomson isometry preserves the geometric mean. Okay, this is an independent question. Actually, this is an algebraic question, because now we have the positive definite cone equipped with this operation, which is not a very simple operation. And we are asking, what are the corresponding isomorphisms? And actually, we don't have a result for general C-star algebras. We have a result only for von Neumann factors. So for Neumann algebras with trivial centers. And on finite von Neumann factors, there is a unique normalized trace, which we will denote by trace. And here is the result, that if we have two von Neumann factors, and we have the positive definite cones, and we have a continuous map between them, without continuity, the conclusion is not true. So this is an essential condition. And we have a bijective continuous map. Then we have two cases. We have the infinite type case, and we have the finite type case. In the infinite type case, you see that those maps are exactly the maps which originate from algebra star isomorphisms or algebra star anti-isomorphisms. Also, the inverse operation can appear here, and we have this two-sided multiplication, the congruence transformations. It's easy to see that any such maps they are preserving the geometric mean. The converse is not easy to show. And the situation is even more complicated in the finite type case. Finite type case, you can think of matrices. And on matrices, there is this functional, which is called the determinant. The determinant is multiplicative, and from that it follows that it preserves the geometric mean. And this shows up, that kind of functional shows up also in the more general case of von Neumann algebras, I mean finite factors. So beside this part, this other part also shows up, which can be considered as a certain power of the determinant. And this is the complete structure. And then, as for C-star algebras, we don't know. We don't know the structure of geometric mean preservers. We have only a certain class of means concerning which we have the structure of mean preservers, and the proof depends on this result concerning order preserving positive homogeneous order isomorphisms. So just two sentences about general means, general Kubo-Ando means. Let me show the shortest way to them. So we have a scalar function on the positive half line, which is operator monotone and normalized by this condition, and then we form this operation, and this is called Kubo-Ando mean, the Kubo-Ando mean corresponding to the function, the operator monotone function f. And there are, okay, let me a little bit change the order. So if we take this function, 1 plus t over 2, or the square root function, or 2t over 1 over t, Then we obtain the three most fundamental means: the arithmetic mean, geometric mean, harmonic mean. This is not a surprise. That is not a surprise. This one is a little bit of surprise. And then, what are the mean preservers? So once again, there are candidates. One can again see that every Jordan star isomorphism, they preserve everything. So they are the best transformations. They preserve everything, so they preserve also the Kuban domains, and once again, the congruences are mean preservers. This is not very easy to see, but this can be shown. And one can think that that's all. No. This is not all, because if I go back to this result, you know, this functional part appeared. So in general, there might be other preservers, but concerning a certain class of means, and those are the so-called power means, which correspond to the, let me see here, correspond to this operator monotone function. So those are the corresponding power means. One would like to define the power mean in the most simple way: a to p plus b to p over 2 and p's root. You can do this, but this is not a good mean. You may like it, but it is not a good mean. This is a good mean. This is the good power mean. And in that way, you get a path connecting the arithmetic mean and the harmonic mean, and when p goes to 0 here, then this quantity goes to the geometric mean. So you have a one-parameter family of means connecting those three fundamental means, and then what is interesting, that we can describe the corresponding mean preservers without any additional assumptions. So if we have C-star algebras, P is not 0, because the 0 case is the geometric mean case, and this is a different case we have seen. But if it is not the geometric mean, but a power mean, in that case, a bijective map preserves that mean if and only if it is of this simple form. So once again, here I don't assume anything, only that it is an isomorphism in the algebraic sense, an isomorphism of the positive definite cone with respect to this operation. And P is just one P, not for all P, just one P. Then this transformation is a composition of a Jordan star isomorphism and a two-sided multiplication. Okay, I skipped the proof, and okay, let me just show you one more operation. This is not a Kubo-Ando mean. This is also a mean, a Wasserstein mean, recently defined by Bhatia, Jain, and Lim. This is the operation. It's not very simple, right? And I can describe the corresponding isomorphisms. Once again, the same form. There is one difference, that here, this C is central. It's a central element. It commutes with everything. And once again, this is a if and only if statement. So it's a precise description. And let me conclude with so this is what I know about mean preservers, applications of the first result that I mentioned, and we can describe using that result about positive homogeneous order isomorphisms. So we can describe the so-called Bure-Wasserstein isometries. And let me mention this result in some details. So maybe this Bure-Wasserstein metric appears also here for matrices, okay? This is that quantity. It is a true metric. It's not easy to see that this is a true metric. if you consider matrices, there is a nice trick how to prove that this is a true metric. But we are interested in the C-star algebraic version of this result. And anyway, for that we need the concept of a trace. This is a positive linear functional, which is tracial. That means that it vanishes on commutators. And we call it faithful if the trace of a positive element, whenever it is zero, it implies that the element is zero. As I mentioned, on finite von Neumann algebras, there are traces, and there are also some kinds of C-star algebras where there are traces, but not on all C-star algebras we have trace, that's clear, but there are classes of C-star algebras, and then we can define formally, it's very easy to define the Bures-Wasserstein metric. We consider this quantity, which is anyway called the fidelity. This metric plays important role in quantum information science, so that's the reason why they call this part fidelity, and this is the definition of the metric. But you know, for matrices, using a trick, one can show that this is a true metric. In the C-star algebra case, it's much more difficult to show that it is a true metric. It was done by Faranik and Rahman for C-star algebras. So this is a true metric, okay? This is a fact, and the question, what are the corresponding isometries? And the result, once again, an if and only if statement. We have that whenever we have two C-star algebras with faithful traces, we have a surjective map between the positive definite cones. Then this is a Bures-Wasserstein isometry if and only if, once again, we have a Jordan star isomorphism, and once again we have a central element such that the transformation can be written in this form. And there is one more condition. So this is a precise description, an if and only if statement. How to prove it? Before that, I didn't mention proofs. Here, just the idea of the proof. The previous proofs were also like that. So the key thing is to use our result on the positive homogeneous order isomorphisms. What do we have to do to use that result? We have to show that our transformation is an order isomorphism which is positive homogeneous. How to do this? Here we have a very simple characterization of the order. So using the Bures-Wasserstein metric. So we have that for two elements A and B positive definite, A is less than or equal to B, if and only if this set of numbers. So those are the differences between squares of distances. Those are numbers. So this set of numbers is bounded from above. This is a characterization. It's not very easy to see, but not difficult to see, that A is below B if and only if this set is bounded from below, from above. But because our map is an isometry, isometry preserves the distances. So our isometry will preserve, will transform this set to the corresponding set with phi of B and phi of A in the place of B and A. And then boundedness from above is preserved because the set is preserved. So we obtain that Bures-Wasserstein isometry is an order isomorphism, and then with some tricks one can show that it preserves the trace, and then if it preserves the trace, then it also preserves this fidelity, and this fidelity encodes positive homogeneity. Okay, it's not exactly positive homogeneity, but it's kind of multiplicative thing. So you can show positive homogeneity, and then you can apply our first result that I mentioned, the basic result. So it is of this form, a two-sided multiplication composed by a Jordan star isomorphism. But there is one more thing, because I said that this two-sided multiplication corresponds to a central element. Why it is central? For me, it was a surprising thing that if we have a Jordan star isomorphism, and we know that this operation, this transformation preserves the trace, and actually this is phi, you see, and I mentioned that phi preserves the trace. So if it preserves the trace, then it forces T to be central. This is, again, a nice argument to show. At least I like that. So to finish, let me remark that quite the same method was applied to describe various relative entropy preservers, Rényi relative entropy, Umegaki, Belavkin, Stashevsky relative entropy in the C-star algebraic setting. And we also have results as a combination of norms and means. I mean preservers of norms of means, but of course I don't have time to speak about them. And let me show the references. Those are the references of that survey paper. That survey paper contains much more results. I mentioned only 2 or 3. Okay. This is Thomson's original result, where he introduced that metric that I mentioned. And thank you so much for your kind attention. Ooh, I was a little bit late.
Okay, thank you very much for the very interesting talk. Are there any questions? Okay, I'll move forward. Yeah. Move away from the speakers. Are there any questions or comments? Okay, Professor Singh.
Okay, so what is the central projection?
This is a projection which is central. Central means that it commutes with everything.
Okay, commute with everything.
So for that reason, okay, let me go back. It's a kind of direct, so what you have seen there, it was kind of direct sum. Yeah, there. So it's a direct sum of this Jordan isomorphism and the Jordan isomorphism composed by the inverse transformation. P is a central projection, so it's a projection.
So that means you put on both, either side is okay.
Yeah. Commutes with everything.
And also you mentioned the continuity, I think, in one of your theorems cannot be dropped. So
this is about the geometric mean. Maybe not here, but later. Yeah. It's essential. That is counterexample.
So does it mean that can it be replaced by another property?
Actually, what is my guess? Okay. As for matrix algebras, okay, as particular operator algebras. So for matrix algebras, maybe you can replace this by measurability or some weaker regularity. Actually, I think that there is a possibility to describe all such transformations, but the description would be more complicated.
So you need some condition, at least, right?
Yeah, and let me continue. If you consider the full operator algebra over a Hilbert space, and if it is infinite dimensional, actually I conjecture that no need to assume continuity. But full operator algebra, Hilbert space, infinite dimension. I don't know the proof, but this is my conjecture.
Okay, thank you.
Thank you very much. Any other question or comment? I have a small question. Like last time that you were in Cadiz, I remember we were talking about in general, central elements of a sister algebra. So they could be, like, depending on the sister algebra, they could be completely different. Like, not.
So in those investigations, no, in my recent investigations, the centrality shows up in several places, and that talk was about centrality. So that was a different thing. Anyway, I recently published a paper, Journal of Mathematical Analysis and Applications, where I collected those results.
I'll look it up.
New kinds of characterizations of centrality, central elements. So you know, I'm doing my work, and centrality shows up in different fields. I mean, that's interesting.
Okay, that was my question. Thank you. Any other question? Okay, so let's thank the speaker again.